Hi everyone, welcome to Frontline Systems webinar on overview of optimization applications in Excel using our advanced products. My name is Dr. Sima Maliki. I am consulting lead and modeling specialist at Frontline Solvers. During this presentation, if you have any questions or comments, please feel free to type them into the chat box to be answered by one of my colleagues or myself by end of the webinars. I strive to remain within the promised time frame, yet to thoroughly cover all the material, sometimes it takes a few minutes longer. I very much appreciate your cooperation. If you're still facing any voice problem or you are not able to see our first slide, that is typical optimization applications, please let us know. As we all know, the optimization applications are widely used across many industries and functional areas. And these are just some of the examples: energy and utilities, chemical, manufacturing, transportation. Furthermore, we would like you to know that many of our customers have found optimal solutions for their large-scale industrial problems that has saved them millions in savings. And this is because building a model can give you insights and also a money-saving optimal solution. But how? So today, we are going to explore how optimization can benefit you in solving your business problems and how to use our tools to build and solve these optimization problems. Together, we'll review typical applications in transportation, financial services, scheduling, staff, and one example of automating optimization using VBA. And that example is in oil and gas industry. What are solvers good for? It is always best and most powerful to efficiently allocate scarce resources arising in your business. It can be your money, equipment, staff time, transportation fleet, or raw materials inventory. These are all resources and they are allocated for some purpose. For example, deciding on which products to ship from factories to warehouses along each route is an allocation of products to routes. In a portfolio optimization problem, we are allocating money to stocks in a portfolio. And in scheduling applications, this is just a matter of allocating people to time slots or scheduling the availability of hospital operating rooms in healthcare application. So, solvers or optimizers are software tools that help you determine the best way to allocate these resources. Now, what you need to do to use a solver or how to define your optimization problem. There are three main steps. There are determining your decision variables, objective function, and constraints. Each problem involves one or more decisions that must be made in order to solve the problem. We call them decision variables, and they are typically numbers reflecting how much of some scarce resource is being allocated to some use or purpose, and that is normally under your control. Now, when we make these decisions, we simultaneously want to satisfy a number of logical conditions or constraints. And there are various types of constraints. Some of them represent limit on your available resources, such as inventory or money. They reflect physical situation, such as non-negativity on variables. You cannot produce a negative number of products. You cannot assign a negative number of people to tasks. Some constraints are determined by policies that you or your organization may set. For example, in a portfolio optimization, you may have a limit on maximum percentage of funds to be invested in any one stock or one industry group. And you might also have balance constraints, like if you have a warehouse and it's a temporary holding point, you want to make sure the flow out of warehouse is equal to its flow in. So you don't want to keep any inventory on hand. And another common element in each optimization problem is a goal or objective that helps you decide which course of action is best. You can determine our objective function by asking what measures are we trying to optimize. The best or optimal solution might mean maximizing profits, minimizing cost, or achieving the best possible quality. Sometimes you may have a combination of them, but our software just take one cell in Excel as your objective. But you can define multiple functions. For example, you want to maximize your profit and minimize a certain cost, and you can combine those functions with using proper constants to have a similar scale and put them in one cell and then define that as your objective. Defining variables and objective function is relatively easy. The main step that takes the most time is usually coming up with all of your constraints, and that is a process. You start with your problem with the constraints that you can think of, and then you solve it, and then you will see that it doesn't make sense, and then you would add more constraints. Now, let's dive in and see how we can solve a problem in practice. This is a transportation application. And in this one, we just want to look at different components of an optimization problem. The problem is predefined. You can find all the examples that I'm going to show today, so don't concern yourself. And all of them are available when you download a trial version of Analytics or platform. So this company has 2 factories, 4 warehouses, and various customers. We want to ship product to two different types of products. And our goal here is to minimize total shipping cost in these layers of the transportation. Oh, excuse me for that. So these color arrows show the potential possible routes of flow between factories, warehouses, and customers. And these green ones show all the potential routes between warehouses and customers. Each arrow here represents a different route. What needs to be decided is how much product to send on each route, and meaning it is under your control. So let's open the Excel workbook and continue talking about the problem in Excel. As you can see, the problem is predefined. This is the Analytics Solver platform driven in Excel. When you download the trial, this is what you would see. If you have a license, you might be seeing a limited version of this. If you have an optimization product, you will only see optimization group. Or if you have risk solver, you should be seeing the same ribbon. And Analytics Solver platform also includes Excel Miner platform, which is our data mining and text mining product. Now, before talking about the examples, let's quickly walk through the ribbon and focus on tools that we'll be using today. Clicking on the Model tab displays or hides the task pane. So this group in the right is called task pane, and it has different buttons. So let's first walk through the ribbon on the top and then the task pane. And in the model drop-down, there are additional options for multidimensional modeling. It's a more advanced type of optimization problems, and it allows you to go beyond the 2-dimensional Excel workbooks. And for that information, we have a very good chapter defined in our user guide. We also have some videos available in our YouTube channel, which I will show you where to find them. Then we have the simulation group. I'm not going to spend time talking about those, but this allows you to define your simulation models. Then we have the optimization group. We have decision variables, constraints, and objective function. Then we have the parameter tab, allowing you to define multiple parameterized optimizations. We have solve action tab, allowing you to run simulation, optimize your models. Then we have create app button. Create app button allows you to convert your Excel models to web or mobile analytics app with Rayson, and you can run your model 3 different ways. You can run it locally on this machine. You can run it on Rayson.com, and also you can run it as in a browser as a standalone web page that is self-contained, which can be the basis of a web or mobile app. Then we have different reports, charts. You can define decision trees, fit distributions. These are more distribution simulation tools. But we have publish button, allowing you to publish your models for use and distribution on the web through Excel Online and Google Sheets. We have our apps available for Excel Online and Google Sheets. Then we have Get Data, allowing you to bring data into Excel from big data using our Apache Spark big data clusters from different files, databases, and worksheets. And then in the Hub, you can look at the examples, user guides, and much more. Live chat. Now, in the task pane, we first have the Model tab. Model tab allows you to view the model in outline form. So we talked about three components of an optimization problem: objective, variables, and constraints. When you define your model, this is the best way to verify you have done it correctly. You can see the objective, the variables, and constraints. You can activate them or deactivate them. Then we have the platform tab, lots of options, how many optimizations to run, and that would come handy when we run multiple parameterized optimizations in the next example. Then here you can set default bounds for your variables and much more. Then we have Engine tab. Here you can select a solver engine and then set its options down here. So all the engines related to a specific solver for you, the problem you pick, are listed here. We also have the option to automatically select engines for you. And finally, we have the Output tab that shows you a log of solution message and also chart of objective. Now, back to our example. As you can see here in this Excel workbook, we have the cost of shipping from factories to warehouses, customers directly. These are just constants and inputs to the problem, and they are not under our control. So these are shipping costs quoted to us by our outside shipping company. What is under our control is decisions about how much to ship along each route at these different locations. So we need to reserve cells representing quantity shipped between factories, warehouses, and customers. So this is how you define decision variables. As you can see, the right side in the task pane, we have 3 blocks of decision variable defined. And you don't see any cell range. That is because our software recognizes name ranges. And if you're not familiar with name ranges, let me show you what I'm talking about. If you want to define cells A1 through C1 as your decision variables, just select them, click on Decisions and Normal. And you can see under Variables in the task pane, now we have A1 through C1 as our decision variables. Now, if you want to define A2 through C2, you can give it a name. For example, var1. Then click Enter. So this block now has a name. And if I define it as decision normal, you can see that the solver recognizes that as our decision variables. So these are called name ranges. I'm sure you're familiar with them, but just to let you know, it's very helpful if you have a larger scale model and helps you, allows you to manage your model. I'm just deactivating this. Let's go back to our example. Now, the objective of our problem is to minimize total cost of shipment along all the routes. This objective is called total cost, again using the name range facility, and then it's defined in cell C91. Let's take a look. We're using some product functions to calculate the total cost of shipping from factories to warehouses. Since the cost coefficient for these routes are defined in cell C10 through F15, we need to multiply this by the total amount of product that will be determined to be shipped. Our decision variables for which we have reserved cells C41 through F46. And similarly, we need to add other costs. Now, we have various constraints in this problem. What restrictions limit our choice of decision variables or the quantity that we can ship between these factories, warehouse, and customers? Capacity of each warehouse, supplies available from each factory, and the demand from each customer need to be considered. So here are the warehouse capacity constraints. We want to make sure what we ship into the warehouses doesn't exceed the capacity of those warehouses. This is the constraint change constraint dialog, and we'll talk about this more in the next example where we define the optimization model from scratch. It has a left-hand side and the right-hand side, and we have a sign here less than or equal to. In the left-hand side, I have all the formulas that I've defined to calculate total which is shipped to warehouses from all the factories, and in the right-hand side, I have the warehouse capacity, which are constants. This is the best practice to keep all the formulas in the left-hand side and constants in the right-hand side. For example, let me show you that how we calculated this for one of the warehouses. You can say that it is just sum of products that are shipped from factory 1 and 2, and we're doing this for separate products, product 1, 2, and 3. And we want to make sure that that is less than the capacity of warehouse 1 for product 1, which is 35,000. And you can define the whole thing as one block. You don't need to do it one by one. Next, we have the factory capacity constraints. Obviously, we don't want to go over what is available. So total that is sent out of factory must be less than factory or available capacity. And similar way, we write a formula to add whatever that's shipped out of the factory to customers or warehouses. We add them all, and we want to make sure for product 1 it's less than 90,000, and similarly for factory 2 and all the products. We want to make sure our demand is satisfied, so you calculate all the possible formulas that will send products to customers. It can be directly from a warehouse or it can be from a factory, and we want to make sure that it is satisfying your demand. It is greater than or equal to the demand. And finally, we have this balance constraint. Whatever is sent to a warehouse must be equal to whatever is going out of the warehouse, just to make sure we are not keeping anything on hand. If you have a different scenario, you might have a cost for keeping inventory in a warehouse, and you can add that to the problem. For now, let's just go ahead and solve this optimization problem by clicking on this light bulb on the ribbon. This is our guided mode. If you haven't used our product, this is a really helpful feature, giving you information in each step of your modeling efforts, and it also helps prevent common errors. When I click continue, two things happen here. First, this model is diagnosed as LP convex, and you can see that another thing that's happening is I have selected the wrong engine. This is an LP problem or linear programming. All the formulas in this model are linear function of our decision variables. So the right engine for solving this problem is LP quadratic, and I by mistake didn't choose that, but this tool is helping me select the right engine. So LP quadratic. LSGRG is a solver for solving nonlinear type problems. And if you're not familiar with all this product structures and what is the right engine, this is a really good tool to help you choose the right one. Or you could also select that automatically select engine option in the engine tab of task pane. So let's click on next step, and now it is letting us know that solver found an optimal solution. Everything, all the constraints and optimality conditions are satisfied. And if you want to learn more about what this message means, just click on this hyperlink. It will open this help and tell you more information about this message. So we achieved what we wanted here, which was to determine how best to ship products between the factories and warehouse and customers, so to minimize our shipping costs, which is now $519,700. After you have used guided mode for a while, and you're solving over and over, and you don't want to sit through, click through all these dialogues each time you're solving the same problem, just go to Help, Operating Mode, and you can see we have three different options available: Guided Mode, Auto Help Mode, and Expert Mode. We suggest you to switch to Auto Help Mode instead of Expert Mode, because Expert Mode totally eliminates the help. In Auto Help Mode, we will only bring up a dialog when there is a problem. Okay, for our next example, we're going to define an optimization model from scratch together. This is a financial services application. We're allocating money to stocks, and this is about an investor who wants to target a specific rate of return for his portfolio while minimizing risk. So again, this is a portfolio optimization. Our goal is to find the best combination of stocks that minimizes risk for a given return. So let's open the Excel workbook and let's look at the data that we have. There's no optimization model defined, and we're going to define it together. And this is usually what happens. You have some data on the Excel and you want to start working on your optimization model. You can just see that I have returns, variance, and covariance between all the stocks, and it's just organized, or the data is organized, and I have just some formulas in the workbook to save some time. Now, in this problem, our decision variables are the percentage allocations of the funds that we can invest in each of 5 stocks. So we need to have 5 cells for our variables. I am planning to use cells C14 through G14, and you can see that I have changed the color around the blue and just make this to percentages, because this wants to hold the percentage allocations of funds to just make it look better. So, and you can see that I've named this block allocations. So when I add this as my variables, you can see the allocations will be used instead of the range of cells. So now we need to let solver know that. So let's use mouse to select this range of cells that we want to define as our decision variables. Go to decisions and normal. So you can see allocations is now added. This is just to verify that you have done this correctly. You can check in the right side. Now, to define the objective of our problem, first we need to create a formula on the worksheet to calculate the measure that we need to optimize. Here, this measure is portfolio variance. Then we need to tell solver whether we want to maximize or minimize our measure and where that formula is. So I have defined a quadratic function at cell C18 to calculate the portfolio variance by a custom quad product function. Now use your mouse to select C18 on the worksheet. Then click on the objective and minimize normal to define C18 as our objective to be minimized. And as you can see, I have name range portfolio variance. So select the formula cell, go to objective, select the type, and use normal. The other options you would see here are for our stochastic optimization type problems, which are covered with our analytic solver platform. You can solve and define them. And stochastic means the problem depends on uncertainty. There is some uncertainty in the problem. What we're looking now at is just deterministic optimization problems. Now, our constraints for this problem. We have 2 types of constraints. We want to make sure the total portfolio equals 100% and that its return is at least 9.5%. For the first constraint, we need to calculate the total portfolio with a sum function over the allocations. Then we need to tell solver that the sum of allocations of the funds to stocks equals 100% or 1. So we have H14 to represent the formula of this constraint. Here it is sum of all the allocations. To make sure this equals 100%, select the cell which has the function sum of all the portfolios. Go to constraints, normal constraints, and here we want to make sure it equals. So let's select equality. In the left-hand side, we can put H14 or total portfolio, my name range, and in the right-hand side, we can enter the value or we can have it in another cell and point to it. So let's enter 100% or just 1. We can add comments and now click OK. This constraint is now added. Total portfolio equals 1. Our second constraint. Total portfolio return must be greater than 9.5%. So we need to set up one cell in the spreadsheet to represent the formula of this constraint. Here I've used cell C20. We have a sum product of allocations and stock returns. Select the cell, then click Constraints, Normal. Now, we want to make sure this is greater than 9.5%. So we select greater than equal to sign. In the left-hand side, we have that cell which includes the formula C20 or portfolio return. And in the right-hand side, let's enter 9.5%. And click OK. Now we have all the constraints. So we have defined our business problem in the optimization language for solver. Let's go ahead and hit the Optimize button. Click Continue. This problem is QP convex. Let's click on or quadratic programming convex. Click on Next Step, and we get the optimal solution. So this is the allocations of funds to different stocks, resulting in minimum risk or minimum variance portfolio that equals 100% and achieves a 9.5% return. This is often called an efficient portfolio. You may have heard of efficient frontier. Using our products, we can construct the efficient frontier rather easily. Here I will show you how. So far, in our example, we have used the solver and found the optimal portfolio with minimum variance for a given target rate of return of 9.5%. Now, let's generalize that. We can utilize parametric optimization to find the efficient frontier that is the optimal solution for several levels of portfolio return. To do this, first we need to define our parametric optimization parameter. So let's select an empty cell like D20, then click on Parameters, Optimization to insert a parameter. This dialog box will open. We are going to define a parametric return rate, and we would like to see the optimal solution for different return values between 8 and 14%, as one of our stocks returns 14%. So let's put 8% for the lower level and 14% for the upper. Let's click OK. Let's go back to Model tab so we can see this parameter is defined. You can see under Parameters, now we have D20. Next, we need to modify our constraint right-hand side to point to our parametric return rate instead of the constant value of 9.5% in the right-hand side. So let's double-click on this constraint, portfolio return greater than 9.5%. Instead of 9.5%, let's click on this button to point to our parametric return rate in cell D20. And you can see that D20 is now selected. Let's click OK. So now we have a parameter as a component of our optimization problem. So if you want to use parametric optimization, you define your parameter, then you have to use it in the optimization. It can be your objective coefficient, it can be in your constraint right-hand side, and much more. Now, we need to do one more thing. We need to tell solver that run, for example, 10 optimizations instead of 1, so that solver finds the solution for different levels between 8 and 14%. So let's go to Platform, Number of optimization to run, and let's set it to 10 instead of 1. Okay, now we're ready. Let's click on Optimize. I'm going to skip guidance, and here are the results. We finished running all of the optimizations 1 through 10. You can look at that in the output section of the task pane. The worksheet will initially display values for the last optimization with return value of 14%. But we can display any of optimization results by changing the selection in the optimization number. For example, we can go to optimization number 1, return value 8%, portfolio variance is 4%, 0.4%, and the allocations. We can go to optimization number 6, return 11.33%, and so on. You could also look at several reports or charts. For example, let's go to Charts, multiple optimizations. We can look at monitored cells. I'm going to select our objective portfolio variance and click OK. This is the efficient frontier plot. We have the optimization index in the x-coordinate, and here we have the value of our objective or variance. You can click on the right section. Additional menu options appear. Let's go to chart options. For the x-coordinate, we have two options: in optimization index or value of our optimization parameter. So if I change it to value of optimization parameter on the x-coordinate, you can see the return threshold. You can use more charts and reports, and this was just one example to show you what is available and how you can define a parameter for your optimization problem and run multiple optimization instead of changing one value and rerunning each model manually. This tool is available to you. So let's close this, go back to our slides for a recap on what we practiced. Modeling and solving problems in Excel spreadsheet. So determine your decision variables, reserve cells for them, define your optimization objective function, and then also your constraints, and just make sure it's best practice to keep all the constants in the right hand side and all the formulas that depend on your decision variables in the left hand side for your constraints. Next, I want to point you to some other features that are available. For example, in your project, you might have yes/no type decisions. You have an allocation problem. You want to allocate something to somewhere, or allocate a person to a job or a task, or you might not. So these are kind of binary type decisions. They only take 0 or 1 values. Or we might have integer values. You don't want to take any positive values. You just want to get whole numbers, 1, 2, 3, 4. And these are called integer variables. And in this example of a type of scheduling problems, I just want to quickly show you how you can use those kind of constraints on your decision variables. Give me 1 second. I didn't open the whole example. So in the first example, we have an amusement park, and that needs a certain number of employees each day of week. Every employee must be on a schedule that gives him or her 2 consecutive days off. How many employees should the park hire, and what schedule should they be on to minimize total payroll cost? So for our employees working 5 consecutive days with 2 days off, we are looking to find the schedule which meets demands from attendance levels while minimizing payroll costs. We have 7 possible schedules, A through G here, with 2 consecutive days off. Our decision variables reflect the number of people hired for each of 7 possible schedules. Now we need to tell solver that the solutions need to be integer values. We're talking about number of people. So we need whole numbers such as 2, 3, or 5 people. To do this, after defining your decision variables, I've already predefined these models to save some time. Just want to show you this whole block is our block of decision variables. Now, to tell solver that these decisions need to take integer values, just select the block of decision variables, go to constraints. You can see the third option is variable type of bound, and then select integer. So go to constraints, variable type, and then integer. This was already defined. The name of this block is employees per schedule. I'm going to remove one of them. We have a constraint total number of people here. And there is another thing we need to do. This is a minimization type problem. We are minimizing total payroll. If we don't tell solver that these decisions need to take positive values, the solver may give us negative values which will reduce the payroll onto negative infinity. So we have to limit that and tell solver we can't do that. So to do this, to tell solver that decision variables need to take positive values, there are two ways. One of them is just select the decision variables, go to constraints, variable type or bound, and then go to greater than or equal to, and set a lower bound of 0. So tell the solver these variables need to take any value greater than 0, positive. Another way, since this is such a common occurrence, we have a shortcut for it. Go to Engine tab. Under each engine, there is an option assume non-negative, and you can set it to true or false. Here I've set it to true, telling solver that all the variables are non-negative. So let's go back to Model tab and delete this extra bound on our decision variables. So for any constraint that relates to your decision variables, if they have a bound, if they are integer, binary, you set a lower bound. If they're all different, semi-continuous, and so on, these are in this group variable type bound. And then if you want to define a regular constraint, just go to normal constraints. These are the points I wanted to make about this example. We can click on optimize. This is a mixed integer type problem, so it is called LP-MIP. And LP quadratic engine can solve this problem for us. So this is the number of people we have to hire for each type of schedule, and total number of people hired is 25. Now, imagine this park has hired these 25 people. We need 2 people for schedule A, B, and all the way to G. We don't need anybody for that type of schedule. Let's go to another version of this problem. We have a second step here. The park has hired the required employees. Now it needs to decide who goes on which schedule. To make this a fair schedule, so we just have 25 people and we know how many we need per day, but we are now working with individual people and we want to know what are their preferences. To collect the preferences, each employee gives us a list with his or her preferences. A 7 means most desired schedule, 1 means the least desired. Now the question is, how should the park divide the schedule among the employees to maximize the preferences? To solve this problem, we have to define 7 decision variables for each of the employees, for 7 schedules, and 1 employee, 7 decision variables. This is kind of assignment type problem within a scheduling problem. We want to assign employee number 1 to one of these 7 schedules. So we define these 7 decision variables, then we decide to allocate only one of the schedules to each employee. Whether to allocate a schedule to an employee is a yes-no type decision. And again, we have an easy way to do this in optimization modeling. We can define the variables as binary, meaning the variables can only take 0 and 1 values. So if one of the variables here takes 1, it means employee number 1 is assigned to schedule F. To define cells as binary, select the whole block of your decision variables. These are all of our decision variables, 7 per employee. Then go to constraints, variable type or bound, and then define them as binary. Now, when you define this as binary, so each one of these can take 0 or 1 values, and it's really easy to define additional constraints. So, for example, we need to tell solver that each employee can be allocated to only 1 schedule. Now it's easy. We can define a sum in this cell over all the schedules assigned to one person and make sure this sum equals 1. So if you go back to Model tab, you can see that our variables are called schedules, and I have this type of constraints. Schedules per employee equals 1. So for each of these employees, we have to sum over all the allocations to different schedules, and we want to tell solver that this needs to be 1. We also have to make sure the employee schedules is equal to required employee. So, and this constraint is defined here, employee schedule equals to employee required. How we define that? So, for each of the schedules, we need to sum all the variables under that schedule. So, if we go down, this is a schedule A, for example. Under schedule A, I have defined this sum, adding all the employees that are assigned to schedule A. And I want to make sure that is equal to 2. This was determined in the previous example. If you recall, you find that we need 2 people for schedule A, 5 people for schedule B. So again, similarly, we sum all the people under schedule B, and we want to make sure that equals to 5. Now let's take a look at our objective function. We want to maximize everybody's preference. So our objective is sum of all the preferences, and we have defined this as total preference to be maximized. Now let's look at how we define or calculate the preferences. We have a sum product of employee preferences. So we are multiplying array of variables by the array of input express preference for each of the individual employees. We add them all together and then maximize that function. Let's go ahead and solve the optimization problem now. Again, it is a LP-MIP, linear programming, mixed integer programming, because we have integer binary variables. Let's click on next step and we get this solution. You can see that each employee is only assigned to one of the schedules. Employee number 1 is assigned to schedule B. The preference is 6. And you can see that most of the preferences are above 5. And if you can also add additional constraints, for example, you want to keep all the preferences within certain numbers and so on. In this example, first we solve the scheduling 1, then we use the values to solve the scheduling 2. There is an easy way to do this, and that's to write a little code and use our VBA feature. So our software allows you to use VBA. Let me show you the slide. More information. So you can automate your optimization model. This is an advanced feature, but I just want to point to that it is available to you. You can run your predefined solver models and control the solver, or you can also define an optimization model from scratch. You can automatically update data, run the model, retrieve the results, and also create an application to distribute to your end users. So, there are various examples available. I'm going to quickly point you to our refinery example. This model is predefined, is a refinery application. This is about an oil refinery that purchases 2 crude oils and are put through different processes to produce petrol and fuels, which are then sold. So our goal is to plan the operations of refinery to maximize our total profit. So the optimization is predefined. We want to control the solver. Let me show you the code. So we have this button to run a macro, and let's go to Developer tab, Visual Basic. Our software you can use object-oriented API, and we could also use the traditional VBA. And we highly recommend you to use object-oriented API to take the most of our recent features of our software. So first, we define an instance of problem by bin prom as new problem. Here we have some additional options showing you how to turn off guided mode. You can pick a solver engine, but you don't really need to do that. You can pick it on the solver. And if you just want to automate the problem, just automate the solver, have bin prob as new problem, prob.solver optimize. And this will run the optimization problem. But here we show you how to set up a parameter, put a message box, retrieve decision variable, final values, reduce costs, and shadow prices with different loops here. And then we also ask for a report and answer report. So let's close this and run this macro. We get optimization status optimized, various final variable values as we requested. Then I'm clicking through this quickly. Then we get reduced costs and shadow prices, and finally we get an answer report as requested. And this example is again available. When you download any of our problems, after installation, go to Help, examples to access all the shipping examples. Go to optimization, examples, and all of these are available for you to review in different applications. So this was an example of how you can use VBA with our products. There's much more you can do. We have a chapter on using VBA. Again, this chapter or user guides are also available using help. So go to help after installation and go to user guides. There are two main user guides that are helpful for you. One is the main user guide. There are various chapters to look into. I'm passing through the basic chapters, which are also very helpful: parameter sensitivity analysis, getting result dimensional modeling, automating in VBA. There are two more chapters that I highly recommend to take a look at: mastering conventional optimization concepts and also building large-scale models. This shows you a lot of hints about spreadsheet modeling and using multiple worksheets and data sources, and it has quick steps toward better performance. So it is really helpful, helps you learn to avoid using non-smooth Excel functions like if, VLOOKUPs, and SUMIFs that make your model non-smooth, and non-smooth problems are hard to solve. You can just get a solution, feasible solution, but not really an optimal solution. And especially this is true when your logical part depends on your decision variable. If you have an if function that is, the logical part doesn't depend on your decision variable, it's fine. It is not really making the problem non-smooth. The result is a constant. So that's one of your the user guides are very helpful. Then we also have engine guide talking about all the engines and different options for them. And we also have a reference guide with more information about the ribbon and all the features available. So let's go back to our slides. Let's quickly talk about our software. You can use our optimization software within Analytics Solver platform, and you could also still access it from Premium Solver platform or Premium Solver Pro. And then we also have Risk Solver platform. If I show you the full picture, you can see what I mean. Analytics Solver platform is our comprehensive product covering optimization, simulation, and data mining. Then we have we also have the specific data mining product like Excel Miner platform, Excel Miner Pro, conventional optimization. For simulation, we have Risk Solver Pro, Risk Solver platform, and so on. You could also do stochastic and robust optimization in Analytics Solver platform and Risk Solver platform. And you can do much more with our products. We have different products available for analytic on the web, desktop spreadsheet, also web server and desktop application in any scale. As I mentioned earlier, many of our customers have found optimal solutions for their larger scale industrial problems. This worth millions in savings. We saw today how building a model can give you insights as well as a money-saving optimal solution. Frontline offers you powerful tools to help you get a better solution by automatically diagnosing your model structure, fixing problems for you, selecting the right solver engine, and providing up-to-date information at each step. For instance, one of these features, the guided mode, today help us choose the right engine in the first example. Now, please feel free to download the trailer of Analytics Solver platform and review the examples. And you are welcome to contact us via this specific number for these webinar attendees. And if you have any questions, you are welcome to email me at consulting@solver.com. I'm sharing my email address with you. And I also want to point you to our YouTube channel. It's called Frontline Solvers. Here's the link to our YouTube channel. So if you go to our YouTube channel, Frontline Solvers, you will be able to explore a lot of demo videos and then go to playlists, different playlists available for you here. Okay, if you have any questions now, please type them in the chat box. I'm happy to answer your questions. Okay, we have to the tab ribbon, operate shortcut right click menu. I don't know, can you expand on your question? So let's go to Excel, for example, open one of the examples. So we have Analytics Solver Platform. We also have this model. In the right menu, you have the options in Excel. If you right-click, you have additional way to add constraint objective if that's what you're referring to, this plus button on the model tab. So this is task pane, model tab. So any right-click menu available. I'm not really sure. Let me unmute you if you can speak. Do you have a speakerphone? You are now unmuted. Hello, can you expand on your question? Hi.
Good evening. I'm trying to see if all those constraints, the variables and the objective functions can be accessed through the right-click menu. You know, like in Excel, you can right-click and do some other things. Is it possible?
So in Excel, you can right-click like this. What do you mean? Is that what you mean? So right-click in a cell?
Yes, you can right-click here. You can see cut, copy, and paste, and all those functions. Is it possible to do all those shortcut menu for all this?
What you can do, this function also works. We have all the list of our functions available here, all the functions in our products. But you can type like PSI, for example, and add a function. That would work.
I get that, but I'm saying put the cursor on any of the background and right click.
No, not like really. If you right click on Excel cell, it will bring you Excel options. The only thing we have available with the clicking is this short.
Okay, that plus. Okay, the
yeah,
plus. Okay.
Yeah,
okay, that's one. Thank you. Okay, you can go ahead.
Problem. Any other questions?
Another question is, what are the problems that one can solve apart from the simple optimization problem with this software?
Okay, so when you install one of our products, you can see that engine limits here. You can solve problems. This is an LP model with 8,000 variable constraints with the basic engine that you have. Now we have customers that solve linear, nonlinear problems up to millions of variables, and the only thing that creates a limit is your memory. So if you have a good computing machine, you can solve pretty much any type of problem. We have additional options for engines available, for example, Groby, extended version of a standard LP quadratic engine that actually you will see here, it is unlimited for variables constraints. We have Nitro engine. So you can pretty much solve any type of problems, linear, nonlinear, and there's no size limit. If you have a bigger problem above these limits, you can add additional engines.
Okay, so the kind of problem I can solve would be based on the information I have on my Excel information, or I can deduce some information from the Excel information given to me and set it up as another Excel. Or how do I, like all those figures you are showing me, how do I articulate it into one and solve it?
So what you can do is you have your information in Excel, and based on the type of constraints, what is your objective, you write some formulas, like imagine you are in Excel, if you want to calculate total cost, you add everything, you define all of your formulas and then define one of them as object. You have to tell solver what are the components of your model.
So I can interpret it from the, let's say the information of things to be solved is in written form. I can put everything into figures, as you have done, like a spreadsheet. I put
exactly.
all the into figures. Then use the constraint, the
three components.
The three.
Constraint, object.
Yeah. Okay, all right. Those are the three to use. Okay, all right. Okay.
Okay, yeah, just put the problem in your Excel worksheet and then use the ribbon to tell the solver what you need for you to do.
Okay, okay. Okay. I will be interested in the risk management also, the Monte Carlo. Is this optimization doing that also?
Yes, so with this product, Analytics Solver platform can do
All
risk,
right.
can cover risk management, risk solver, or risk analysis, and Monte Carlo simulation. You can see the simulation model distributions, correlation, and results. We didn't cover that today because today our
Okay, okay, all
webinar
right.
was on
So it's
optimization.
okay.
Tomorrow, same time, we cover simulation and risk analysis.
Okay, so I would like to join that too because
Okay,
I'm
I'm going
more
to
into
share
risk
the link
management.
right now. I'm going to share the link
Okay, all
for
right.
everybody. Is welcome to join us tomorrow for
Okay,
our simulation and risk analysis webinar.
okay, all right. I will join tomorrow.
And you could
All right.
also
So
solve
every
stochastic type. Yes, go ahead.
okay, okay, okay. So everything is all in this application. Everything, the distribution, the the
Yes.
transportation, the assignment, the scheduling, everything I can go through.
Yeah, you can define any type of problem with this tool, but you have to define it for the solver. So, but you can solve any
Okay,
type of transportation, allocation, any type of problem with this
okay,
tool.
right, all right, all right. Okay, thank you.
Thank you, sir. Okay. I
Okay.
shared the link for webinar for tomorrow.
All right, okay, I will
Feel free
check
to
that.
email me at consulting@solver.com if you didn't get it. Thank you very much, everybody. If anybody else has any questions, please raise your hand and I can unmute you, or you can just type in the chat box. Thank you very much. Have a wonderful rest of the day. Again, you are all welcome to join us for our webinar tomorrow, same time, on simulation and risk analysis. We also will look into solving a simulation optimization, stochastic optimization problem. And again, please feel free to contact me with any questions at consulting@solver.com. Bye for now. We appreciate your time.